Okay, hello everyone, welcome back to another video. This is a video on all the topic 9 questions that I could find in all the 2019 high-level papers. So we're going to start off with the May 19 time zone 1 high-level paper. Question 6 is simple harmonic motion, which is part of topic 9. So, and there's a little bit of Doppler effect in it as well. So looking at a pendulum, and they're showing us the graph of its kinetic energy, and we have to calculate the length of the thread. So we of course remember that the period of a pendulum when it's oscillating at small angles is 2 pi root length over g. So we can find the length of the thread if we can just read off the period. So we have to read off the period, and we have to be a little bit careful because this is the kinetic energy that is being shown. So we have to remember that maximum kinetic energy is when the pendulum whizzes past the equilibrium position. So we start off at time 0, it's whizzing past the lowest point, and then when the kinetic energy is 0, it reaches, say, all the way out to the left. It reaches the maximum displacement from equilibrium on one side. Then it swings back and it passes the lowest point again, and then it swings all the way over to the other side. So we haven't reached one full period yet. It's only when it then falls back and swings by the equilibrium a second time, then we know one full period has been completed. Okay, so the period is 2.25 seconds. And then we can work out L as 2.25 squared divided by 4 pi squared. And then we are multiplying by G, which, well, in Hong Kong is 9.79. So you can also just write 9.8 there, and then you're going to get something along the lines of 1.26. Let me try. I didn't even do it with the Hong Kong number. Let me just see what I get. I should get the same. 1.26. Yeah, 1.26 meters. Notice they want you to state your answer to an appropriate number of significant figures. So that third mark is actually for rounding it off properly. If you use 9.8, you just have to round it off to 1.3, 2 sig figs, and that's not too difficult. Label on the graph with the letter X a point where the speed is half that of its initial speed. Okay, so we know, of course, that kinetic energy is proportional to speed squared. So if we say v prime is the speed when it is half of its initial speed, so v prime is half v, say v is its initial speed, the maximum speed, then v prime being half v, we're squaring it, so we're going to get a ratio of 1/4. So that the kinetic energy, when it has half its initial speed, the kinetic energy is 1/4 of its initial kinetic energy. And since it's 20, well then we are looking at the point here, which is 5 millijoules. That's X. Okay. The mass of the pendulum bob is 75 grams. Show maximum speed is about that. Okay, so we can read off it has maximum speed when it has maximum kinetic energy, of course. So 20 millijoules is maximum kinetic energy, which is when the speed is maximum. Then we can rearrange that to get this. 0.075 kg. Remember to convert grams to kg because we're working with joules and meters per second and all that. And you get 0.73 meters per second, which is about 0.7. Remember to show some more decimals than just the 7. so that you actually show you have calculated it correctly. Okay, so now we have sort of a small topic 2 question. Here in this topic 9 question, we have to do a little bit of collision theory. So the bob collides with a small stationary object, it has same mass, and then they stick together. Of course, that's an inelastic collision, totally inelastic, they stick together. Calculate the speed of the combined masses, conservation of momentum. So we have the momentum before the mass times the speed, which is given to us as 0.8. And that has to equal the double the mass, the momentum afterwards, which is both masses moving at speed v. And then you get 0.4 meters per second, half the speed. Okay. Show that it's inelastic. Okay, well, we know that the definition of an inelastic collision is that the kinetic energy is not conserved. So it's the usual calculation of kinetic energy after, kinetic energy before. Got half 2m 0.4 squared, which gives us something like 0.012 joules. That's the kinetic energy after the collision. Before the collision, we had more kinetic energy. We had this amount, which is 0.024, twice as much. So the Ke is not conserved. Hence, inelastic collision is the definition. Pretty simple. Okay, then we have to sketch the variation of gravitational potential energy. And they've shown us the variation of the original kinetic energy when we just had one bob. But we now know that, well, we know that the gravitational potential energy is, of course, opposite to the kinetic energy. So if you just had the one bob swinging, then we know that when you had minimum kinetic energy, you have maximum potential energy. All the kinetic has been converted to gravitational potential energy and so on. But we know that the kinetic energy actually halved after the collision. So now we only have half the amount of kinetic energy that we had before the collision. So we can only reach half the maximum of the gravitational potential energy. So it's going to go like this. And we can graph that like this. That's how the gravitational potential energy of the two bobs is going to be changing over time. And then it suddenly jumps to a Doppler effect question. Speed after the collision was measured using a sensor, probably an infrared sensor, like the motion sensors that you probably have used in class. The sensor emits a sound that is reflected off the moving object. That reflected sound is detected. It has a slightly different frequency, and it's from that difference in frequency that it actually determines what the speed of the moving object is. But we have to explain why those frequencies are different. So you basically have to explain the Doppler effect. So that goes something like this. We can write that the sound reflects off a moving object. So the object becomes a moving source of sound. And in that case, the wavelength changes. You know, the wave fronts get compressed in front of the moving object. But the wave speed is the same, therefore the frequency changes, and that is the Doppler effect. So let's write it down. The sound reflects off a moving object. And thus the wavelength changes. Since the wave speed is constant, only depends on the medium. This will change the frequency. This is a case of the Doppler effect. Okay, don't forget to name drop Doppler, because they haven't actually referred to the name Doppler effect at all, so you want to show that that that's what this is about. So the sound reflects of a moving object, thus the wavelength changes. Since the wave speed is constant, this will change. This is a case of the Doppler effect for a moving source. Okay. Okay, then we move on to May 19, time zone 2. Question 8, we have monochromatic coherent light incident on 2 parallel slits, and initially they have negligible width. Don't need to worry about diffraction. This is only going to be 2 source interference in the beginning. And they are coherent, so they had constant phase difference, single frequency, single wavelength. Lower slit is covered at first, okay. M due to the upper slit alone is 22. Now we uncover it, and what is the intensity? Okay, so we're going to get constructive interference, right? So at M, equidistant from the 2 slits, we get constructive interference. So at M, we can say M is equidistant from the slits, from each slit. So constructive interference will occur at M. The amplitudes add, okay, and we know, of course, it's the same light source that is producing light coming out of the 2 slits, so they have the same amplitude, and when those amplitudes add, then we're going to get double the amplitude, and since the intensity we know is proportional to the amplitude squared. So since intensity is proportional to amplitude, when the net amplitude doubles, I is 4 times larger, quadruples, hence I is going to be 4 times 22, 88 watts per square meter at M. Okay. Then we have now a simple one, which is just they give us P is the first maximum on one side, so the distance MP is the S in our double slit interference formula. And we know the distance between the slits, we know the distance to the screen. Notice distance to the screen much greater than distance between slits, so we can use the approximation that is this. And we can easily find the wavelength. Just plug in everything. 10 to the negative 3, D 10 to the negative 3. Big D 1.5, and then you get something like 5.6 10 to the negative 7 meters, which is 560 nanometers. That sounds about right. The width of each slit is then increased, so now the width is no longer negligible, so you're going to get the diffraction effect. Single slit diffraction is going to occur through each slits. So why will P now be less than M? Because you get that diffraction envelope that modifies the intensity of the interference pattern. So due to single slit diffraction, a diffraction envelope will now modify the interference intensities. Okay, so they sort of get a bit, the intensity decreases a bit as you move away from the center. Show that due to single slit diffraction, the intensity at a point on the screen at distance 28 millimeters from M is 0. Okay, let's do that. Well, we know that the first minimum in the diffraction pattern of a single slit diffraction occurs at this angle. We know what the wavelength is, and we know what the width of a slit is now. So that gives us this angle, small number of radians, and that is the angle that sort of points to the first minimum. And we can then see how far away is that from the middle by just doing some simple trig. So we are 1.5 meters away, and the first minimum occurs at this angle. And then how far away are we from the center on the screen? That's x. So tan theta equals x over 1.5. So x is 1.5 times tan of that angle we just got, and you get something like 0.02799, which is roughly 28 millimeters. So that's one way of doing that. Okay, then the November paper, there was a question 10, which was on thin film interference, part of topic 9. And here we first have to predict whether X undergoes a phase change, and that has everything to do with, of course, knowing the indices of refraction going from air into magnesium fluoride, which has this index of refraction, and then the lens, which has this index of refraction. So the light ray X is bouncing off a layer with a higher refractive index, so it is going to undergo a pi phase change. That is when we get the pi phase change, when light goes from or reflects off a material with a higher refractive index. So yes, it will undergo a pi phase change because it reflects off a material with higher refractive index. Okay, just wanted to note then take a look at this point down here at the second layer. You actually also get a pi phase change. So Y is also going to undergo a pi phase change when it reflects off the second layer, and that's going to be important in one of the following questions. So be aware of that. Okay, and now we're looking at normal incidence. Okay, that's the only case we study in the diploma physics course where the angle is the angle of incidence is 0 degrees. So you have to imagine this light ray coming in vertically, and in that case the path difference is just going to be 2D, right? It just just goes straight through the magnesium fluoride and bounces off the second layer and goes straight up again. So the path difference is just 2D. Calculate the smallest value of D that will result in destructive interference. So now this is where it's important to know that the light ray Y also undergoes a pi phase change at the bottom layer. So also pi phase change for Y. So the condition for destructive interference becomes, if they've both undergone a pi phase change, then in order to get destructive interference, the path difference in the medium needs to just be a half integer multiple of the wavelength. So, so you actually have to be very careful using the formula that is listed in the data booklet, because here we have the following. So it's 2dn, where n is the refractive index of the material in which the light is traveling, and in order to get destructive interference we have to have a half integer multiple of the wavelength. And if we're looking for the smallest value of d, then we are looking at the path difference being as small as possible, so it has to be half a wavelength, and then we can work out what d is, and it's just half the wavelength over 2 times the refractive index, and if you do that you get 190 nanometers. So slightly tricky, this one, because you can't just blindly use the formulas given in the data booklet. You really have to think about this one. And then the practical advantage of this is, so what we're doing is we're basically reducing the reflection of a given wavelength so that more light passes through the lens into the camera. So the reflection of a given wavelength is reduced, and more light passes through the lens. We want the camera to collect as much light as possible through the lens. Okay, so there you go. Okay, there's still some more questions here. Yeah, now we get into the Rayleigh Criterion and so on. They also just want you to show that you know how to draw a single slit diffraction pattern. So we're looking at the pupil of the eye. We have the diameter of the pupil. So when light travels through this small opening, then light undergoes diffraction, and we know that we have a bright central peak that then goes to a minimum, and then we have equally spaced out secondary, or all the minima are equally spaced out, but the secondary maxima, remember, are much smaller than the central maximum. So practice drawing out this single slit diffraction pattern. You need to know how to do that nicely. Estimate in rad the smallest angular separation of 2 distinct point sources. Okay, so the Rayleigh criterion, of course, so the Rayleigh angle is the smallest angular separation at which we can distinguish and resolve these 2 point sources. And because the diameter is a round opening, we have to multiply lambda over b by 1.22. So remember that. If you have a rectangular slit, it's just lambda over b, but a round opening is 1.22 lambda over b. And we then just plug in what we know, and the diameter is 2.8 millimeters, right? So is that like this? Yeah, 0.0028 meters. And then we get around 2.9 10 to the negative 4 rad. That is the smallest angular separation that allows us to resolve the 2 point sources. Okay, that's it. Bye.